We're just about finished with our equilibrium unit. In our last episode, you were asked to create a model that demonstrates on a molecular level the effect that temperature changes have on the equilibrium between nitrogen dioxide and dinitrogen tetroxide. So let's get back to our class and see how your models compare to the ones our students came up with.
Okay, let's see the models that you made. Who would like to go first?
That's ours. Our model shows that at cold temperatures, there are more molecules of N2O4, and at high temperatures, there are more NO2 molecules.
At negative 79 degrees, we show heat being removed, which shifts the equilibrium towards the product. At 100 degrees Celsius, more heat is being added, which makes equilibrium shift towards the reactant.
I like that. It also looks like you've shown the gas molecules farther apart at higher temperatures, and that's great. So how did your model go?
Well, we did ours a little different. We tried to show how the change in temperature would affect the energy levels.
There are lots of different types of models, so I'd expect yours to be different. What's important is that the information is correct. And I see that you've drawn N2O4 at a lower energy level than NO2. Can you explain why and explain your model a bit more?
Sure. The reaction's exothermic, and that means the energy level of the product, N2O4, is lower than the energy of the reactant.
And the higher the temperature, the more kinetic energy the molecules have, and the closer they get to activation energy.
The product molecules have much higher activation energy to reach than the NO2 reactant molecules. At low temperatures, N2O4 molecules probably don't have enough energy to make it all the way up to the activation energy and convert to NO2. So there'll be more N2O4 than NO2.
At high temperatures, more N2O4 molecules have enough energy to reach the activation energy and convert back to NO2. So there will be more NO2 at higher temperatures.
You've all made some really great points with your models. And models are always a work in progress. So as scientists learn more, the models will change. But regardless, this is excellent work.
Before we wrap up this unit on equilibrium, I thought it would be interesting to hear from someone who uses chemical equilibrium in their job every day. So I spoke with Deanna Oser, Program Manager of the Ambient Monitoring Program for Georgia. Ms. Oser works for the Georgia Department of Natural Resources Environmental Protection Division Air Monitoring Branch. Scientists in her laboratory monitor nitrogen dioxide levels in our air, along with many other measurements of atmospheric chemicals. A lot of cities face significant challenges due to high concentrations of ground-level ozone, nitrogen oxides, and fine particulate matter in the air. And she was able to elaborate on those challenges. Take a look. Thank you so much for joining us, Deanna. We're glad you're here.
Thank you for having me.
Now, you work for the Georgia's Ambient Air Monitoring Program.
That's
You're the
correct.
manager there. Just so we're all on the same page, can you tell us what ambient air is?
Sure, it's the air that you breathe outside. Okay. And that's different from like indoor air or air coming out of a factory. So EPA just classifies them each a little bit differently.
Gotcha. Now, tell us a little bit more about Georgia's Ambient Air Monitoring Program. Who you work with, what you do there.
Sure. We are made up of about 40 different scientists, and we work all over the state of Georgia. We monitor for about 200 different things at about 40 places across the state of Georgia. And we do this for multiple purposes. One of them is to see if we're meeting EPA's requirements, because they set standards for what healthy air is for about 6 different major pollutants. But we also measure some precursors for the ozone. We also measure toxic compounds to make sure that we can tell the people of Georgia how their air is they're breathing.
Now, our students did a performance task related to the measurement of smog.
Okay.
Can you tell us a little bit more about smog? What are the components and what are the sources of smog?
Sure. Smog is made up of many different things. You have particulate matter, which is very fine particles, almost microscopic, 2.5 micrometers. And 30 of these will fit across the width of a human hair, if you can think about it that way. So it's very small. It gets trapped down in your lungs. So it's a health standard that they've set. It's also made up of nitrogen oxides, which comes from burning of fuel. And it's also made up of volatile organic compounds. And what this is carbon-based compounds that have a very low boiling point, so they become gas at room temperature. You might be familiar with them as paint fumes.
Okay, we see those VOC warnings on paint cans and...
Right, and diesel exhaust, you smell it, toluene. And it also comes from vegetation. And the third component of smog is ozone, and that's formed from VOC and oxides of nitrogen. And nitrogen oxides come from combustion or burning of fuels.
Okay. Now I'm curious because we think of trees and plants as being really good for our air quality.
Absolutely.
But as you just mentioned, VOCs come from trees and plants.
That's right. So in Georgia, we have a problem because we have a lot of forest and a lot of plants. Well, these plants give off certain kinds of organic compounds. And when EPA sets the standards, we still have to account for these. So as much as we can do for the industry and for the cars and reductions, we still are going to have the trees because we don't want to be without those.
course.
We actually monitor a site up in the North Georgia mountains at Fort Mountain, and it's nothing more than to see what the ozone is in the forest up there.
Sort of a control area.
That's right. We call it our background ozone site.
Great. So trees, great for cleaning the carbon dioxide out of the air, but they
Absolutely.
do have that VOC
That's
component.
right.
And so there's a balance.
There
You
is,
need to
and
have
when
a balance.
EPA sets a standard, they set it for the whole nation. So we may have more ozone from the trees, whereas out west they wouldn't. And so there's a very fine balancing act they have to do.
Interesting.
Mm-hmm.
Interesting. Now, I hear you talking about ozone levels.
Mm-hmm.
We know that ozone at ground level is dangerous.
That's right.
But then we hear about the ozone layer in the stratosphere.
That's right.
Is that different?
It's actually the exact same ozone. It's formed naturally in the stratosphere. However, when it's formed down on the ground level, it comes from a reaction of these oxides of nitrogen and these volatile organic compounds in sunlight. So we have ozone in the summertime. And the problem with it down on the ground is it's actually harmful to our respiratory systems. So in the summertime, if you have asthma or if you have breathing problems, you might find it harder to breathe on days where the ozone levels are higher. EPA likes to say ozone is good up high, but bad nearby.
Good up high, bad nearby when it comes to ozone.
That's right.
an easy way to remember it.
Absolutely.
We talked about how tiny the particulates of smog are.
That's right.
How do you measure the levels of smog, and how do you measure what's in the air?
Well, it depends on what we're looking for. So for particulate matter, since they're actually particles, we can collect them on a little filter. We let the gas pass through, the air pass through, and we collect the particles, and we weigh it before and after. So it's just
Very
gravimetric.
simple.
Absolutely.
Yeah.
But for some of the others, we use, for the volatile organic compounds, we might use a gas chromatograph for those. For the nitrogen, we'll actually excite electron by adding ozone, of all things, to make it excited and measure the energy it gives off there from the light. And for ozone itself, we actually measure the absorbance of the wavelength.
Gotcha.
So
Interesting.
it's very fascinating.
Yeah, that's very, very neat. 3 different ways to measure the different particulates or the different
And that's
compounds.
just 3. There's every pollutant is measured a different way.
Right. Now, is there a place that our students could go to see this data and see air quality and see what's in the air right now?
Absolutely. You can go to our website, which is amp.georgiaair, all put together.org. And that's our website. And what we do there is we actually have measurements we take 24/7, 24 hours a day, 7 days a week, and we put our data up there for the public. And the purpose of that is so that they know how their air is doing. And it's all color-coded based on EPA's levels for what clean air is.
Like those when we have the smog alerts. and-
Absolutely.
okay.
So if you hear a code orange day, that means that the forecasting team, which is made up of some of my staff and some scientists from Georgia Tech, that they are actually have predicted that the levels are going to be above the safe levels for all citizens to breathe. And so if you go to our website under Air Quality Index, you can see what the codes are and who should be careful that day.
That's really powerful information.
It is. It's wonderful.
That's great. Now, let's talk about what the impact an individual can have on air quality. Is there anything that one person can really do to affect the overall air quality of Georgia?
You think if I'm going to drive myself today, it's not going to make much difference, but actually it does. Because we have seen over the course of years that everything we do builds up to make a difference. So on days when it's a code orange day, we've asked you not to fill up your gas tanks before 6 p.m. and to drive in carpools. And actually that makes a difference. On days we've predicted code orange smog alert days, when everybody's done their part, we've actually had no violations that day.
That's great. And so, like my car emissions test every year, it actually is really important.
It is very important because what it's looking for is those VOCs and the nitrogen oxides, and it's making sure that your car is running clean enough. And when you put just your car on the road, you think about your car plus all the other millions of cars in Atlanta, it makes a big difference.
That's right. All that traffic also adds up to all
Yes,
that
it does.
air pollution.
And we actually have monitors right beside the road to see how the interstates are doing. So it's pretty fascinating.
And have you noticed a change in recent decades with the work that your organization and the EPA and at large has done?
Absolutely. We've been monitoring ozone for about 40 years. And in the last couple of years, in the last 10 or 15, we've seen it drop drastically over the time from about 80 parts per billion down to about 73 parts per billion right now. And every time EPA gets new data, and finds more information, they may lower the standard trying to clean the air. So while we may be currently in compliance, it's a moving target.
Sure, but we're moving in the right direction.
That's right. And for particulate matter, all the cleaner fuels and the changes we've made to our various industries across the state have really made a difference. So they've dropped by about half now.
Wonderful. So it's the impact the individual has and those larger
Absolutely.
EPA standards for plants and things.
So all those regulations you have to deal with really do make a difference.
That's good to know.
Absolutely.
Good to know. Now tell us a little more about your background. How did you end up here?
Well, I had a wonderful chemistry teacher.
Oh, that's a good plug for this program.
Yes. And she excited me about science. I loved science, and she just made it fascinating. And so when I went to college, I became a chemical engineer, and I started working for the state in monitoring right out of college.
So it's fair to say you've been a science nerd your whole
Forever.
life.
Yes.
And you're embracing it.
Absolutely.
That's wonderful. Well, thank you so much for joining us today. It was
Thank
very
you.
exciting. And your takeaway from today, pay attention in chemistry class.
Amen.
And do your part to clean the air.
Absolutely. Absolutely.
Okay. Thank you. That concludes our unit on equilibrium. But you don't have to be done yet. You can check out the closer look section for Unit 10 for additional material related to equilibrium. When you're ready, come back for Unit 11, our unit on nuclear chemistry, one of the most exciting topics of science.